Okay, so today we start it's not a new title, it's a continuation of the Fourier series. It is the complex Fourier series. So remember, before we did the Fourier series of the function, it is simply a node plus the sum from 1 to infinity an cosine nx plus bn sine nx. This is the Fourier series of the periodic function of period 2 pi. Of course, we extended this to any function, to any period, but for now it's enough to talk about functions of period 2 pi, and I'm sure you've already seen that different periods do not change any major computations. It's the same idea exactly. Now, what do we mean by the complex Fourier series? Let's recall a very basic but a very important formula, what's called Euler's formula. It's one of the most beautiful and interesting formulas in mathematics. It is e to the I theta is equal to cosine theta plus I sine theta. So what is I here? It satisfies I square equals -1. So usually people write it as I equals root -1. I don't like writing it this way because when we deal with complex numbers and when we talk about root of -1, in fact root -1 has two values. It's I and -I. So I just avoid writing it as much as I can. If I can avoid it, I would just not write it. So I square is -1. First, let me explain why Euler's formula is true. So if you like, we can say justification of Euler's formula. And then after justifying Euler's formula, why is e to the I theta equal to cosine theta I sine theta, we will go and see the complex Fourier series. So if you are familiar with the Euler formula, and if you don't like seeing the justification, you just can forward the video and see right away the complex Fourier series. But for those of you who are not familiar with this formula, let's just talk about it very little. What is e to the I theta? Remember, we have the Maclaurin series of e, which says e to the x is x. Now x is I theta over n factorial, right? Now what about if we extend this sum, okay, just to show you the full picture. So when n is 0, this is just 1. When n is 1, this is I theta. When n is 2, you get I square, but I square is -1. So basically this becomes negative theta square over 2 factorial. When I is 3, you get I cube. Now what is I cube? What is I cube? It's I square times I, but I square is -1, so this is -1 times I, so that's -I. So I cube is -I. That means you're getting -I theta cube over 3 factorial. Then plus I to the 4. What's I to the 4? I to the 4 is I square, but I square is -1. When you square it, you get 1. So this is plus theta to the 4 over 4 factorial. What do you expect next? You will have plus I theta to the 5 over 5 factorial, then minus theta to the 6 over 6 factorial, and so on. So this is what you're gonna get after expanding a few terms of this series. So I think now you're seeing the idea. Now I have some terms that have I and other terms that do not have I. So if you collect all terms that have I that do not have I, these are 1 minus theta square over 2 factorial plus theta to the 4 over 4 factorial, and so on. Then what are the terms that have I? These are theta minus theta cube over 3 factorial, 5 5 factorial, and so on. And now if you agree, the first quantity, this is a quantity containing the even power, this is exactly cosine theta, then the other quantity is sine theta. So this is the justification why. Okay, so having done the Euler's formula, let's see now how to move from the real Fourier series to the complex Fourier series. What we mean by the real Fourier series is what we used to call the Fourier series. So the real Fourier series, we mean a node plus the sum from 1 to infinity an cosine plus bn sine. Okay, this is what we mean by the real Fourier series. What we mean by the complex Fourier series is introducing the e, because the e has a complex exponential, e to the I theta. So before going to that, what is Euler's formula again? The Euler's formula says e to the I theta is cosine theta plus I sine theta. If you replace theta by negative theta, this becomes e to the negative I theta equals cosine negative theta plus I sine negative theta, right? But the cosine cancels the negative sine, and the sine takes the negative out, so this becomes negative I sine theta. So this is e to the negative I theta. This is it, right? So now if you add the two boxes, what you get is e to the I theta plus e to the negative I theta equals 2 cosine theta, from which you find that cosine theta is e to the I theta plus e to the negative I theta over 2. And if you subtract the two boxes, so e to the I theta minus e to the negative I theta is 2I sine theta, which means that sine theta is e to the I theta minus e to the minus theta over 2I. Okay, so we found cosine and sine in terms of the complex exponentials, while the original Euler's formula tells you the other way. You're finding the exponential in terms of sine and cosine. Okay, so now what we're doing, now the plan of the following computations. The computations are easy, they're a little long, but the idea is we will go back to the Fourier series. This is my Fourier series, and we will replace every sine and cosine by these quantities, and we'll see what happens. Okay, so now we expect the Fourier series to have these complex exponentials, and that's the reason it's called complex Fourier series. So what happens is this. So then the Fourier series becomes a node is just a node plus the sum from 1 to infinity of what? An. Now what is cosine nx? You have cosine, this is, don't forget, this is cosine theta, right? So if you say cosine nx, you replace theta by nx, so you get e to the I nx plus e to the negative I nx over 2. Then a plus bn, and for the sine, you have e to the I nx minus e to the minus I nx over 2i. Okay, all of this is inside the sum. After that, I'm going to write the sums as a node plus, first of all, you have 1 over 2 out, so you just take it out. You have the sum from 1 to infinity an e to the I nx plus an e to the minus I nx plus 1 over I bn e to the I nx minus bn over I e to the negative I nx. Okay, so this is what you have now. My next step is I'm taking the positive exponentials. So if you look here, you have an e to the I nx and bn e to the I nx, and also I'm taking the negative exponentials together. So I will have a node. This is a node, plus I have half the sum from 1 to infinity. So again, I'm taking these two terms together here, I'm taking these two terms together. So what we get is, so what we get is an plus bn over I e to the I and x, right? Then I'm taking the other negative exponentials together. So what are the negative exponentials? You're taking, of course, everything is multiplied with half. It's an minus bn over I e to the negative I and x. Is it okay? So we took these two terms together. We took these two terms together. Okay. Now what is this? So at this stage we can see that all terms are written in terms of the exponential except for the a node. The a node is a number. But even the a node, I can write it as, just to make things unified, to make things have one form. The a node is a node e to the I 0x, right? So plus the sum from 1 to infinity, an. If you agree, the bn, so this is not to forget the 2, the bn over I is negative ibn. So let me explain this here. So I have bn over I. If you forget the bn, so let's look at 1 over I in general. 1 over I. Just remember this. We don't like seeing the I in the denominator. Remember this. Everywhere, we don't like seeing the I in the denominator. What is the meaning of I? Remember, I is, roughly speaking, the square root of negative 1. Again, I told you why I avoid using I as root negative 1. So what we do, we multiply with I and with I in the top and in the bottom. So you get I over negative 1, which is negative I. So basically, 1 over I can replace it by negative I. This is what I did in the first sum. Then a plus. What about the other sum? It's from 1 to infinity. So following the same idea, it's an plus I bn over 2e to the negative I and x. Fine? Okay, so this is this. We are almost done. After that, what I'm going to take is, I want to write one sum. So instead of saying a node plus the sum from 1 to infinity, I forgot. I forgot the exponentials here. So we're seeing e to the I 0x, then we're seeing the sum e to the I n x, then another sum e to the negative I n x. I want to have one sum for all of this, okay? So the point is to have one sum for all of this. I'm going to the last sum here, and I'm going to replace, so let's do them here. I'm going to replace the negative n by k, which means n is negative k. Now what happens in this case? When n is 1, because my sum starts from 1 to infinity, when n is 1, k becomes negative 1, and when n is positive infinity, the k becomes negative infinity. Okay? So this sum becomes the last sum. So this is a node e to the I 0x plus the sum from 1 to infinity an minus ibn over 2e to the I n x. This did not change, plus the sum. Now an, this is the 2, okay? Now an plus ibn, but what is the n? It's negative k. So this is a to negative k plus ib negative k e. So instead of having negative n, this will be I kx, because we changed the negative n to the k. And the k starts from negative infinity, ends at negative 1, right? So this is what we have. Now, whether you're using k or n as your notation, it's irrelevant. What we mean is, if you have the sum, n from 1 to infinity, or let's say to 2, n squared, this is 1 plus 4, right? And if you have the sum k from 1 to 2, k squared, this is 1 plus 4. So whether you're adding n square or k square or t square or anything square, you're getting the same value. I mean, if you go back to our sums and you say, okay, I don't like seeing many notations. I don't want to see the n and the k, so let's unify them again. So I'm going back to the k. So this is the k. And I want to replace every single k back to n, okay? So let's delete the k and just replace it by n again. Okay, so this is what we have. Now, what is the meaning of this last line? If you say, okay, Cn is A0 when n is 0, An minus Ibn over 2 when n is positive, I mean n is 1 to infinity. I took this from here, from this sum. And then if you say Cn is A negative n plus Ib negative n over 2 when n is negative. If you say this, what happens? This first term becomes C0 e to the I0x. This first sum becomes Cn e to the I nx, because this quantity here, An minus Ibn, when n is positive from 1 to infinity, you denoted this thing by Cn, right? This is what we did. Okay, so this becomes this, plus the sum, and from negative infinity to negative 1, Cn again, e to the I nx. So now what do you have? You have, look what do you have? You have the sum from negative infinity to negative 1. So just imagine you have the real line. This is the real line. You're adding all numbers from negative infinity up to the negative 1. Then you're adding the 0 term. Then you're adding all terms from 1 to infinity. So basically it's like adding all numbers from negative infinity to infinity, right? So this is what we want to write. So now I'm going to this last line and we're saying, okay, this is equal to one sum from negative infinity to infinity Cn e to the I nx. Where, so what are the Cn's? These are the Cn's. Okay, so this is our Fourier series. So the complex Fourier series. So in the end, please, what did we do? We started with the Fourier series in terms of the sine and cosine. We replaced the sine and cosine by their values in terms of the complex exponentials. Then we simplified up to this point. So please, I'm writing. So in the end, the summary. If f is of period 2 pi, its Fourier series can be written as, this is very simple form. It's much easier, by the way, than the first form. And this is one of the advantages in general in using the complex numbers. What distinguishes complex numbers is, okay, the computations may look difficult, but in the end, when you reach your forms, usually we have easier forms than the real form. So in the end, after all the simplification, what did we reach? We reached this, right? So in the end, what we are writing is that the complex Fourier series is just the sum from negative infinity to infinity Cn e to the I nx. But what is the Cn? The Cn is here, okay? I'm not copying it here, okay? So I'm just leaving this line empty just a little, and let's see what is the Cn. So the C0 is A0, right? But what is the A0? It's 1 over 2 pi, remember, from negative pi to pi, f of x dx, right? Okay. When n is positive, what is the Cn? Let's look. What is the Cn when n is positive? It's An minus Ibn over 2, right? This is our definition here. This is it. So this becomes, take the 1 over 2 out. This becomes, what's the An? It's 1 over pi, integral from minus pi to pi, f of x cosine nx dx, minus Ibn f of x sine nx dx, right? But okay, so this is equal to 1 over 2. You can take the pi as a common factor. you can have one integral from minus pi to pi f of x times, if you agree, cosine nx minus I sine nx dx. But what is this? Let me write it in the same page, or we can move to the next page. Now, what is this this thing? This is exactly e to the negative I n x. So in the end, we have Cn equals to this integral. So in the end, we have when n is positive, Cn is 1 over 2 pi times the integral f of x times e to the negative I n x dx. This is what we have when n is positive. What about, so please remember, I'm trying to write the Cn. I didn't write it right away. I'm just doing some manipulations, and you will see why. We started with the C node. This is what happens when when n is positive. And now we want to see what happens when n is negative. When n is negative, what is the Cn formula? We go back here. When n is negative, this is my formula. It's a negative n plus I b negative n over 2, right? This is my formula. And please, now we're saying when n is negative. So for example, when n is negative 1, this a becomes a sub 1. We don't have a meaning for a negative 1. It is a1, a2, a3. But the c's can have negative sub indices. So now the point is this is equal to, this is the 1 over 2. The a negative n is 1 over pi integral from minus pi to pi f of x cosine negative nx dx. Remember, the a n formula is this integral with cosine nx, then plus I times the integral. So the b negative n is the integral f of x sine negative nx dx. But what is this? This is 1 over 2 pi. Again, you can take the pi out. You can have one integral from negative pi to pi, f of x as a common factor. Then you will be left with cosine nx, because again, the cosine cancels the negative sign. There is no need for the negative sign. But the sign gives you an extra negative sign. So this becomes negative I sine nx dx. And this is 1 over 2 pi integral minus pi to pi f of x e to the minus I nx dx. Fine? Is it clear? Okay. Now please look at this. So what is this? This is Cn when n is negative. What is this? This is Cn when n is positive. They have exactly the same form. This is very interesting. Cn has the same form, whether you're dealing with positive n or negative n. But please, we're not saying they are equal. They have the same form. And because n is positive, when you substitute here, for example, you substitute n2, the exponential becomes e to the negative 2. But here you can't substitute 2. If you substitute negative 2 as a negative number, the exponential becomes positive 2. So they are different, but nicely, they have the same form. This is very interesting. And this is, again, one advantage in using the exponential form. Okay, so when n is positive, it has this. When n is negative, it has this. What about the 0? If we go back to the 0, this is the C0. I think you all agree that this is equal to 1 over 2 pi integral minus pi to pi f of x e to the minus I0x dx. Again, I'm trying to reach one form, one unified form for everything. So now if you write the C0 this way, e to the minus I0, then you look at the positive case, e to the minus in, and the negative case, e to the minus in, then you say, okay, what is the Cn formula? So now back and writing the summary. What is the Cn in the complex Fourier series? It has only one form, 1 over 2 pi, integral from negative pi to pi, f of x e to the minus inx dx. That's it. It's very interesting that we have only one form in the complex Fourier series. If you compare this with the real Fourier series, when we have the sine and cosine, if you remember, we had 3 formulas. We had a formula for a node, we have a formula for a n, and a formula for bn. Now the complex Fourier series, you just have one formula, and a shorter series. Even the Fourier series in the complex case, it's much shorter when you write it than the real Fourier series. This is why we're gonna use a little the complex Fourier series, and we will see its connection later with the Fourier transform. So this is the new form, the complex series, and these computations justify to you how we got to this form.